We solved the clues, fit them just right, but some models give us the fright. Let's fix that with regularization. Hello, welcome to Algo Talk. Today we'll explore what is regularization and why is it important. Imagine you are a detective solving a case, but why does detective need regularization? Sometimes detective gets too excited and tries to pick up every single clue. But some clues are just noise. When we use all the clues, we might end up overthinking the case and get the wrong solution. That's where regularization comes in. It helps us focus on the important clues. If you focus on every tiny detail, like a coffee stain on the desk or a missing button, you might miss the big clues like a witness statement. Suppose the detective has 5 key cases. He fits a line, solving the case using a single clue. But when he faces a new case, is his solution good enough? Could the detective do better? Is the detective reading too much into the clues from the training case? Or is the training case enough to solve the mystery? If you want to explore linear regression in detail to understand what it lacks, check out our channel or click the link in the description. Detectives' challenges with linear regression. Multicollinearity is like having clues that are too similar. When clues overlap too much, it's hard to tell which ones are really important. Imagine having multiple witnesses who tell the same story over and over. It's hard to know which witness details are crucial. Overfitting happens when the detective gets too caught up in the details of the training case and ends up with a solution that doesn't work well for a new cases. It's like a detective who is focused on a single case that they forget how to handle other cases. High variance is like sometimes the detective's solution changes drastically with different sets of clues. This means the detective's findings aren't consistent. Picture a detective who comes up with different conclusions every time they get a new set of clues, making their result unreliable. Choosing the right clues is tricky. If the detective picks too few or too many clues, they might miss out on solving the case properly. Think of a detective who either collects too many clues or skips important ones, leading to either confusion or incomplete solutions. We need a special guide that helps the detective focus on the most important clues, keep the investigation balanced, and avoid getting sidetracked by unnecessary details. This is where regularization helps. Regularization reduces the importance of redundant clues and keeps the detective from getting too caught up in every detail. Ensures the detective's findings are reliable across different cases, as well as helps in selecting the most important clues or ignoring the rest. To understand the concept better, we use 5 random data points, each with 9 features, to train the model. It's like training a detective with a few cases that all share the same set of clues. We will also measure accuracy on both training and test data using RMSE. This helps us see how well our detective performs on both known and new cases. Let's break down how linear regression helps us solve the case. We start with all the clues for 20 cases to train our detective. These clues help us uncover patterns and relationships. Linear regression finds the best line that fits these clues against final verdict. Our fitted line helps us predict the outcome based on the clues. Here's the formula representing the model's final verdict. This formula combines all the clues. We have to make predictions. Each clue contributes a certain way to the final outcome. Think of this formula as the detective's toolkit, where each clue has a specific role in solving the case. The coefficients determine how much each clue helps in reaching the final conclusion. These numbers show how accurately our detective solved the cases and how well the solution works for the new cases. Note: perfect solution would have RMSE equals 0. Now that we have seen our detective's clues and final verdict come together, let's dive into some challenges that might arise along the way. First up, we'll tackle the issue of multicollinearity, a sneaky problem where clues overlap and make it hard to solve case clearly. Multicollinearity in linear regression is like having two witnesses who always tell the same story. Imagine you are trying to determine which witness provides the most useful information, but since they both say the same thing, it's hard to figure out who is really helping solve the case. In regression, you use several clues to solve the case. If two or more clues are closely related, they end up taking over each other, making it difficult for the model to determine which clue is truly important. If two clues are too similar, the model gets confused about which one is more important. Even if both clues are useful, their impact on solving the case becomes unclear. The weights showing each clue's importance becomes unstable. Small changes in the data can lead to big changes in these weights, making it hard to trust the model. If two clues are too similar, it's like trying to figure out which twin caused the effect. It's tricky to know who did what. To uncover the mystery of multicollinearity, we use a tool called VIF. It's like our detective's special magnifying glass for spotting overlapping clues. VIF helps us measure how much a clue's role is inflated because it's closely related to other clues. It reveals which clues are too similar and might be overlapping in their information. How to use VIF? Treat each clue separately. Consider each clue as an independent variable and all other clues as dependent variables. Calculate R2 score for each clue. Compute how well it predicts the others. Time for some results. Our detective has used the VIF tool to uncover which clues are overlapping and causing trouble. Here are the results of our investigation. Clues with high VIF values like clue 4, clue 7, and clue 8 are highly correlated with others. These are the troublemakers that might be causing confusion in our case. Think of these VIF values as a detective's list of suspects. High VIF values are making too much noise and need to be investigated closely to ensure they aren't mudding the case. Now that we know which clues are causing trouble, let's see how removing them affects our case. Features like clue 8, clue 4, 3, 7 and 9 with high VIF values contribute significantly to multicollinearity. Removing them sequentially shows their impact on model's performance. Regularization is like giving our detective a special tool to keep clues under control. Here's how it works compared to regular linear regression. In normal linear regression, our detective tries to use all clues as they are, even if some clues are too similar or conflicting. This can lead to confusion and unreliable results. Ridge regression adds a penalty to the size of the clues. Think of it as telling our detective to be careful and not let any single clue dominate too much. This penalty helps keep the clues balanced and reduce the confusion caused by too many similar clues. Ridge regression makes sure that no single clue has too much influence, leading to more stable and reliable results. By controlling the clues, our detective can focus on solving the case without being misled by too many similar details. For a deeper dive into ridge regression and how it works, check out our separate video. You can find the link in the description. For now, let's stick to the basics of regularization. Ridge regression offers a way to handle multicollinearity while keeping all clues in play, providing stable and reliable results. Now we understand multicollinearity. Let's move to overfitting. Overfitting happens when our detective gets too focused on every tiny detail in the training cases, learning not just the patterns but also the noise. Instead of understanding the bigger picture, it ends up memorizing irrelevant specifics. When this happens, the detective excels at solving the cases it already knows but struggles with new cases. It's like memorizing answers for one mystery and failing when faced with a different one. By adding a penalty to overly complex solutions, techniques like ridge, lasso, and elastic net ensures the detective doesn't get lost in irrelevant details, keeping the focus on solving the mystery in general terms. Detective finds a good generalized solution by trading off just a bit on the training cases. High variance occurs when the detective becomes overly sensitive to the clues. Even small changes in the training cases make the detective's conclusion shift dramatically. It ends up learning too much from the specific details of the cases rather than focusing on general pattern. If you remove or change some training data, the model's performance on test data changes significantly. The detective might solve one case well, but struggle with a similar one because it's too reliant on the specific clues from the original case. This tendency to memorize rather than generalize leads to overfitting. The model shines on the training cases but performs inconsistently on new data. To dig deep into this issue, we trained the model several times, each time removing different parts of the training data. We measured the RMSE on both the training and test data to see how the model's performance changed. In technical terms, we calculated the variance, which in this case is quite high, specifically for test cases. Ridge regression adds a penalty proportional to the square of the coefficients. This discourages large coefficients, smoothing out the model's predictions and reducing its sensitivity to training data changes. Lasso regression adds a penalty proportional to the absolute value of the coefficients. This can drive some coefficients to zero, simplifying the model and making it more stable by focusing on the most important features. Having explored how regularization tackles issues like high variance and keeps our model stable, let's now focus on another critical aspect: feature selection. Just like a detective who needs to decide which clues are worth following and which are just noise, we need to be selective about the features we use in our model. Not every clue helps solve the case. Some clues might be irrelevant or redundant, making the investigation more confusing. Lasso regression acts like a detective who removes irrelevant clues. It shrinks the importance of unhelpful clues to zero, focusing only on the essential ones to solve the case. Lasso regression helps streamline the investigation by removing unhelpful clues, ensuring the detective focuses on what really matters. In this case, it has removed all the clues except clue 2 and clue 4. Now that we have compared our detective tools, let's ensure we avoid common pitfalls when using them. Even the best detectives can make mistakes. So, it's crucial to be aware of these common misconceptions to solve our cases accurately. Using an overly large penalty can lead to a model that is too simple, missing important patterns. It's like a detective ignoring too many clues just to keep the case file clean, which might cause them to miss critical evidence. Lasso regression doesn't always pick the best features. It may discard important ones if not fine tuned correctly. Imagine a detective who, due to a flawed method, misses out on crucial clues while focusing too much on others. Applying too much regularization can strip the model of useful information, making it less effective. It's like a detective removing so many clues to avoid confusion that they end up with too little information to solve the case. Linear regression is simple, straightforward, and easy to interpret, but can get misled by noise, struggles with too many clues, or highly correlated ones. Ridge regression, though, stabilizes our detective's clues and handles correlated clues well, it doesn't help in pinpointing the essential clues. All clues stay in play. Lasso regression sharpens our detective's focus by zeroing in on crucial clues that simplifying the case but might overlook important clues if they are closely related. Elastic net combines the best of Ridge and Lasso, balances clue stability and selection and also effective with many clues. But it is more complex and needs careful adjustment of two parameters. Thank you for staying with us till the end. We hope you enjoyed solving the mysteries of regularization in a fun and engaging way. For detailed explorations of ridge, lasso, and elastic net regressions, check out the links in the description. If you found this investigation insightful, don't forget to subscribe for more detective work on data science topics. Like the video if you enjoyed it, comment with your thoughts or questions. Stay curious and keep unraveling those data mysteries.